So in this video, we're going to discuss oblique asymptotes. But what we're going to do first is discover how they come to be. So we're going to look at what we know about horizontal asymptotes first. So let's say I gave you the function y is equal to 2x plus 1 divided by x plus 5. If I give you that function and ask you to tell me what the horizontal asymptote is, we know that since the degree in the numerator is equal to the degree in my denominator, that this is going to have a horizontal asymptote at y is equal to the coefficient in front of the numerator and the coefficient in front of the denominator, so at y is equal to 2. Okay, let's take a look over here. Let's say I gave you y is equal to 6x squared plus 8x minus 1, and that's being divided by 2x squared plus 9x. And if I asked you again to tell me what the horizontal asymptote is, you take a look at the degrees. Since again the degrees are equal, then you would tell me, oh, the horizontal asymptote then occurs at y is equal to 6 divided by 2, which of course is y is equal to 3. Let's do one more. Let's say I gave you y is equal to x squared plus 3x plus 1 all over x cubed, oops, that's a cubed, plus 2x squared plus 5x plus 7. And if I said, what's the horizontal asymptote here? You would say, oh, in this case, the numerator degree is less than the denominator degree. So my horizontal asymptote would then occur at y equals 0. Now keep in mind that what the y equals 2, y equals 3, and y equals 0 are telling us is how the function is going to behave as x approaches positive infinity and as x approaches negative infinity. In this case, the function is going to try and approach y is equal to 2, in this case y equals 3, in this case y equals 0. Okay, so we know that. But I want to go back and just see if we can find a relationship between these three. So what I'm going to do is I'm going to take 2x plus 1 and divide it by x plus 5. So 2x plus 1, I'm going to divide it by x plus 5 and see what I get. Okay, I'm going to change colors here because it's very exciting. Here we go. So x goes into 2x 2 times. 2 times x gives me 2x, and 2 times 5 gives me 10. And I subtract. 2x minus 2x is 0. 1 minus 10 is negative 9. And x does not go into negative 9, so I have 2 with some remainder. Okay? Okay, take a look over at this one. Let's do the same thing, same idea. I'm going to take 6x squared plus 8x minus 1, and I'm going to divide it by 2x squared plus 9x. So 2x squared goes into 6x squared 3 times. 3 times 2x squared is, oops, I didn't change colors, but I hope you're okay with that, is 6x squared. 3 times 9x is 27x. We do the math, and 8x minus 27x is negative 19x. And pull down that minus 1, and let's try it again. 2x squared does not go into negative 19x, so therefore I've got a remainder here of negative 19x minus 1. Okay, let's do it one more time over here. Let's take x squared plus 3x plus 1, and we're going to divide it by x cubed plus 2x squared, I should have made this one smaller, plus 5x plus 7. And how many times does x cubed go into x squared? Well, it goes in 0 times with a remainder of a whole bunch of stuff. Let's see if we can see a relationship between our quotient and our end behavior. In this case, our end behavior was y is equal to 2. All of our function is going to approach y equals 2, and I found a quotient of 2 before the remainder. In this case, I've got a end behavior of y equals 3, and I had a quotient of 3 before the end behavior. And in this case, I had y equals 0, and I had a quotient of 0. So in other words, I can determine the end behavior of my function by dividing the numerator by the denominator. Okay, So let's try one more thing. What happens if I give you this function? Y is equal to x squared plus 3x minus 4, and we're going to divide that by x plus 2. Now, if I asked you to tell me about the horizontal asymptotes, you would say, oh, Miss McQueen, the numerator is greater than the denominator, so therefore there is no horizontal asymptote, and you would be correct. But there is still end behavior, and let's figure out what the end behavior is. So we're going to do the same thing we did before. We're going to take x squared plus 3x minus 4, and we're going to divide it by x plus 2. So we say to ourselves, x goes into x squared x times x is x squared, x times 2 is 2x. And we subtract. 3x minus 2x leaves us with x, pull down the minus 4. X goes into x one time. 1 times x gives us x, 1 times 2 gives us 2. And when I subtract, I get negative 4 minus 2, which is negative 6. So I get x plus 1 with a remainder of negative 6. But based on what we've learned up here is that the value that I get for my quotient before the remainder is going to give me the direction of my end behavior. So therefore, what we just figured out is we have an oblique asymptote at y is equal to x plus 1. Well, what is y equals x plus 1? Well, x plus 1 is the equation of a line with a slope of 1, we get that from right here, and a y-intercept of 1, we get that from right there. Well, let's see what this is going to look like on a graph. So I've got my x and y axes, and what I need to do is to put in my oblique asymptote. Now my oblique asymptote is going to go through the point y is equal to 1. So let's say that's about there. And it's going to go at a slope of up 1 over 1, up 1 over 1. So it's going to do something like that. Okay? And of course I have to label it. So we're going to label it y is equal to x plus 1. Now if I was going to graph this function, take a look up here. Let's graph this function. We need to set up the other fences and probably factor it. So I'm going to bring that down here. So let's factor the numerator. So it's going to be x plus 4, x minus 1. Factor the denominator. Oh, doesn't need to be factored. And we're going to talk about our fences. So we have a vertical asymptote at x equals negative 2, because x can't be 2, negative 2. And we're going to have an oblique asymptote at y equals x plus 1. All right, so let's get that other fence in there, which is at x equals negative 2. Well, if that's 1, that's 2. Like that. Okay, and of course I need to label that. So I'm going to label x equals negative 2. Good. So these are our new fences. Our new fences, one's oblique though and one's vertical. All right, so let's see what happens. We need some points to tell us what else is going to happen with this graph. All right, so the next part is going to be our points. And let me get a different pen out to do our points. So let's start off with our x-intercepts and our y-intercept. The y-intercept's easiest, so I'm going to start with that. The y-intercept, I make x equal to 0. It's probably easiest way back up here. So 0 plus 0 minus 4 and 0 plus 2. So my y-intercept is going to be negative 4 divided by 2, which is going to be at negative 2. So let's put that in. If that's 1, then that's 2. So we'll put it in at, this is the point, 0, negative 2. Good. Okay, our x-intercept, we're going to make our y 0. 0 times x plus 2 is just 0. So 0 equals x plus 4 and x minus 1. So we're going to have two x-intercepts, one at negative 4 and one at positive 1. So an x-intercept at negative 4, there's negative 2, so negative 4 is going to be way over here. So this is the point -4, 0. And I'm also going to have one at x equals 1. So this is the point 1, 0. Okay, and now my points are going to try and get as close to those asymptotes as possible. So this function is going to look something like, it's going to go through those points, and then closer, closer, closer to this vertical asymptote there, and closer and closer and closer to this oblique asymptote there. Nothing's happening in this part of the fence, but we come on over here, and again, let's just extend this a little bit more so we can see what's going on. In this case, we're going to approach the vertical asymptote here, and we're going to eventually make it down here to the oblique asymptote way down there. So this is a bit of a smoother line. Something like that. Okay, and so this is our rational function. It's a little bit stretched because of the oblique asymptote. Okay, so how do I know that a rational function is going to have an oblique asymptote? Well, in summary, an oblique asymptote occurs when the degree in the numerator is exactly one more than the degree in the denominator. That is, the numerator degree is the denominator degree plus 1. So for an example, if I had the function y is equal to x cubed plus 2x plus 1 over x squared plus 5, in this case, because the numerator degree is 1 more than the denominator degree, we would have an oblique asymptote. Okay, or if I have y is equal to x to the 5th minus 7 over x to the 4th, in this case, I'm going to have an oblique asymptote because it's exactly one more. And that's all you need to know about oblique asymptotes.